Okay, thank you, Robin, for the kind introduction. Good morning, everybody. It's a great pleasure to be here at this very interesting workshop. Thank you very much for the invitation. It's an even greater pleasure to present the latest results on the single atom resolved probing of strongly correlated systems. The experiments I will be presenting were done at the Max Planck Institute for Quantum Optics in Garching, and although I'm now at the University of Strathclyde in Glasgow. Well, from the time the first computers were invented, physicists were intrigued by the question whether computers can simulate any physical system perfectly. But well, we learned very quickly that it is very complicated and very difficult to simulate especially strongly correlated systems. And we found that to simulate certain systems, the computational power grows exponentially with the number of particles involved. And this turned out to be a severe restriction in understanding of particular physical systems, and it was a real difficulty, and nobody found a way out of it, how one can solve this problem in principle. But then in the 80s, Richard Feynman came up with a revolutionary idea of a quantum computer, that indeed a computer must use the laws of quantum mechanics to simulate other quantum systems. So the general idea of this quantum computer or quantum simulator is that you create a well-controlled quantum system that can simulate the behavior of another quantum system. And one particular example for this will be throughout many of the talks of the workshops, are atoms in optical lattices or ultracold atoms in general. These atoms in optical lattices, I'll say a few more words later, like these optical lattices are created by pairs of intersecting laser beams, and the ultracold atoms are held in sort of egg box shaped potential wells basically, and the atoms can hop from lattice side to lattice side with a tunnel coupling J and have an on-site interaction pretty much as electrons can move in certain real materials in the potentials created by ions. And the beauty of these ultra-cold atom systems is that many of the experimental parameters are tunable, and you can probe the system, as I will be reporting in this talk, with a precision and even with single atom and single lattice site level that is virtually impossible in real materials. And that raises the hope that these quantum simulators can help us to answer unsolved questions in quantum many-body systems. While one prime example is I think the 2D Fermi-Hubbard model, which is conjectured to be the key model for high-temperature superconductivity. And we hope that these experiments will shed a deeper insight and help us to understand these and many other interesting phenomena in these strongly correlated systems. Well, today I will be talking about, like in particular, on single site and single spin resolved imaging of strongly correlated systems in optical lattices. And well, I'll first show you how we can apply these techniques to imaging strongly correlated mod insulators, and then we go from the zero tunneling limit to finite tunneling, and I will show you that we were able to see quantum correlated particle hole pairs, and then by doing parameter quenches, sudden changes of the system, we were even able to see how correlations spread across the system in with a light cone-like spreading. And then from the mere observation of these systems, we will be doing something more active, which is flip individual spins in the mod insulator, and then we can not only flip the spins but also see the dynamics. And in particular, I will present one of the latest results, which is the dynamics of a mobile single spin impurity, which we could track with this quantum gas microscope I will be showing to you in a second. So, as it is a mixed audience, not everybody is familiar with optical lattices. I'll have one introductory slide on optical lattices. So basically, these optical lattices are created by laser beams, which in our case are ready tuned to the atomic transition. So, the simplest optical lattice you can imagine is created by two counter-propagating laser beams, in our case at 1064 nanometers, that creates an optical standing wave with a periodicity of half this wavelength, and the atoms can basically be trapped in the intensity maxima of this standing wave. And here you can already see one of the difficulties when one wants to resolve individual lattice sites, as the spacing is 530 nanometers only, and that is compared to the wavelength, to the fluorescence, to the resonance wavelength, or in our case of rubidium atoms, of 780 nanometers. So one has to find a way how to discriminate these rather short distances, and you'll see in a second how we can do it. And this concept of optical lattices can easily be extended from one dimension to two dimensions. So in 2D, if you have two pairs of intersecting laser beams, you'll end up with an array of tubes. These signify the intensity maxima. And in 3 dimensions, you'll get, in this case, a cubic lattice structure, like with a cubic arrangement of individual intensity maxima. And in the following, we will only be using a single layer out of such a 3-dimensional optical lattice. And we create this 3D lattice by again having 3 pairs of intersecting laser beams. One comes from above and is reflected off this mirror, which is a mirror for the lattice wavelength, and transmits the fluorescence light of the atoms. And there are 2 other pairs of laser beams in the horizontal plane that create the square lattice structure on top of that. And here you can already see the key ingredient of the experimental apparatus. As I said, we want to resolve atoms on neighboring lattice sites. For that purpose, we designed a very high resolution optical imaging system with a numerical aperture of 0.68, and we obtain at 700 nanometers a resolution of roughly 700 nanometers, which is almost the same as the the spacing between 2 lattice sites. And typically all the experiments I will be presenting in the following, they start with roughly 1,000 rubidium atoms in a single antinode of this vertical standing wave. So basically they are trapped in a plane, as I said, onto which we impose this lattice structure from this horizontal lattice beams. And the way we detect the atoms in the optical lattice is by fluorescence imaging. So typically all the experiments are done with rather shallow lattices measured in recoil energies, typically 10. That's where there's still some finite tunneling between the different lattice sites. And then before we detect the atoms, we basically freeze all dynamics, and we make the lattice suddenly very deep and increase the lattice depth to roughly 300 microkelvin. And then we illuminate the atoms with a near resonant laser field and optical molasses. And the effect of this molasses is twofold. On the one hand, the optical molasses continuously cools the atoms and holds them in place. And on the other hand, the atoms continuously scatter photons from the optical molasses, and we emit them. And with the imaging system, we have a position resolved detection. And typically we collect by this 5,000 photons per atom in 1 second. And this is a typical fluorescence image of a thermal cloud, and each white spot is an individual atom, so you can very clearly distinguish them. And like the white spots designate the lattice sites. And one particular feature of this fluorescence detection is that we have light-assisted losses, light-assisted collisions. You have to keep this in mind when you see all the pictures and data in the following throughout my talk. Please keep this in mind. It's very important for the understanding. So the idea is, or what happens is, whenever there are 2 atoms on a single lattice site and they're illuminated by the optical molasses, they very quickly undergo a light-assisted collision and leave the trap even before sufficient fluorescence photons are detected. So that means when we have initially only 1 atom on a lattice site, nothing happens. If we have initially 2, we detect them as an empty site. If we have initially 3 atoms per site, 2 of them leave the trap, and we only detect them as a single atom. So basically what we are doing, we detect the parity of the atom number, or we measure the occupation modulus 2. So please remember this. And so let's right away jump into the physics. So we want to study the strongly correlated systems. We start with a Mott insulator, and as we consider bosons on an optical lattice, we use the Bose-Hubbard model to describe this system. So it consists of this Hamiltonian consists of these 3 terms. On the one hand, there's the tunnel matrix element J that characterizes the strength of coupling, of tunneling from one side to another, and these A dagger and A are the atomic creation and annihilation operators on side I and J. And then another term is the on-site interaction. As the atoms repel each other, it costs energy to hold them onto a single lattice site, and that's characterized by this on-site interaction U. That's basically, and these N are the atomic number operators that count the number of atoms on a lattice site. And this third term characterizes the external harmonic confinement. And in the following, we will be starting by considering just the atomic limit, where the tunneling is basically completely suppressed. And then we are basically deep in the Mott insulator regime. So what describes the physics of this term is the ratio between J and U. So if the tunneling is very large compared to the on-site interaction, we are in the superfluid regime, and we can, for example, have a Bose-Einstein condensate in the lowest band of the lattice, and that's completely delocalized over the whole optical lattice. And if, however, the interaction dominates over the tunneling, we're in the Mott insulating regime. And we'll start with that. So in the Mott insulator, let me just introduce to you what you will see to interpret the following pictures. So as I said, the optical lattice is made by out of laser beams and create that's this interference pattern created by the laser beams, but the laser beams have a finite size, and that leads to this external harmonic confinement. And something very interesting happens if we now try to fill the lattice with atoms, and the system tries to find the lowest energy state. So if we fill the system with atoms, they first occupy the lowest lying energy states, and if we want to put more atoms into the system beyond this particular point, we could either put another atom at the outer part of the system that would cost like this amount of potential energy, or it is in this case more advantageous to put a second atom at the center of the system and fill the inner part of the system with 2 atoms per lattice site before more atoms come in at the outer part. And this leads to the formation of these Mott shells many of you have come across. In this case, we have an inner shell of 2 atoms per site surrounded by a shell of 1 atom per site. And let's see whether we can see this with the microscope. Here you can see 2 images of such Mott insulators with different atom numbers. So they look quite different from the picture of the thermal atoms you have seen before. So we see that the atoms are very, very densely packed here, with, as you will see in a second, with 1 atom per lattice site. And then here you see this ring structure with some empty lattice sites here. And initially there have been 2 atoms per lattice site in the center. As you remember, there are these light-assisted losses, so the doubly occupied sites are detected as empty sites, and this is surrounded by a shell with 1 atom per lattice site. And we can use a computer algorithm and the knowledge that uses the knowledge of the point spread functions of the images of the individual atoms to deconvolute these images and get basically a digital information out of this. And we can do this deconvolution with very high fidelity, and we end up with just a distribution of atom or no atom on a lattice site. And what you can see here already by eye is that we have a very low defect density here. We can map out individual defects, and the unit and the probability of finding 1 atom at the very center of these shells is very high. And I should point out the beauty of this digitalization, basically this deconvolution going from the real images to the digitized ones. By this method, we basically get rid of all technical noise from these images, and we are only left by statistical uncertainties, basically governed by the number of atoms these images. And you also notice that they are really nice and round, so we can determine the center of the images and then do azimuthal averages along these circles. And we have a closer look at the atom number and the atom number variance as a function of the radial distance from the center. So here you can see, like what you already can see by eye, basically that the atom number goes to 1 at the center of this n equals 1 shell, and then basically drops. And more interesting is the atom number variance. So you can see that at the center of the mod insulator shell, the atom number variance drops to 0, indicating or directly showing number squeezing, and that the atom number variance goes to its maximum value in between or at the border between the two shells and at the outer part of the system. And this behavior can be readily understood with a very simple model in the zero tunneling approximation and we can find an analytic expression for the probability of finding n atoms at a radial distance r from the center. That's this function, and it has and one can fit this model to the data. That's this red curve, and as free parameters to this fit, we can in particular extract the temperature of the system. And with this method, we can for the first time do in situ thermometry of these mod insulators in optical lattices. That was not possible before, and for this particular system we obtain, for example, a temperature of 0.07 times U over Kb. That has to be compared with the melting temperature at which the compressibility vanishes for the mod insulators. That's at 0.2 U. So with this we can prove that we are really deep in the mod insulating limit. And what I should also point out is that this curve, this model, fits all the data points within the error bars, and that tells us that as far as we can see, the system is in global thermal equilibrium. Also, let me stress again that these data points are from a single shot only, so we can do thermometry on single samples. And also, again, like this radial distance, I would like to draw your attention that this is the distance in micrometers. So you can see here the changes of the variance of the atom number on the scale basically of a lattice side. So this feature is only 1 micrometer wide, and we can probe the statistics, the atom number statistics with this method with really unprecedented precision. Now,
can I ask one question?
Sure.
You say this is from a single shot, but
yeah.
But the variance is not determined from a single shot.
Yes, it is from a single. The data you see
from the azimuthal behavior. Is that how you do it?
Yes. So the question is this indeed a single shot? Yes. And the variance is basically the variance of the atom number in a radial bin. So when we do this azimuthal average, we have a number of atoms in this bin, and we can compute the variance in this bin, and that's basically this value and the error bars. And the error bars are just determined by the number of atoms we average over in this azimuthal average. That's also why we have a larger spacing of the points for shorter distances, because otherwise we wouldn't have enough points. But this, indeed, the data you see here is particular from this picture, and no other picture, not averaged over several other of these pictures. And we can do this like for any of these pictures, and they look very similar. Okay, so what you have seen now was the mod insulator in the atomic limit, where the tunneling was completely suppressed, and now we should have a closer look what happens when we allow tunneling, when we tune J over U. So, and in the following, I will also restrict myself to one-dimensional systems. So for what you have already seen in the atomic limit, where we have no tunneling, basically the ground state of the system is like rather boring. So we have ideally no fluctuations and perfect unit occupancy, 1 atom on every lattice side. However, when we allow tunneling, quantum fluctuations appear, and these quantum fluctuations lead to a virtual hopping of particles to another lattice side and back. And these quantum fluctuations, they lead to these correlated particle hole pairs. I call them particle hole pairs in the following, as like they are actually like an empty side and a doubly occupied side. But throughout the talk, I call them particle hole pairs. And they basically, these quantum fluctuations appear everywhere on every lattice side. So this sum runs over all lattice sides with a probability amplitude J over U. So this sort of signifies the quantum state. And in contrast to these quantum fluctuations, there are thermal fluctuations, which, however, are spatially uncorrelated. And when we increase the tunneling, more and more of these particle hole pairs proliferate, and they eventually extend in size, and they lead to a deconfinement of these pairs at the transition from a mod insulator to a superfluid. And the question is, can we directly see these quantum fluctuations? I should also say these quantum fluctuations, they're really fundamental. So they would also appear at 0 temperature. So, and that basically drives the transition from the mod insulator to a superfluid, which, as you know, is a quantum phase transition that would also occur at 0 temperature. And the goal of this experiment is to answer the question, can we really nail down these quantum fluctuations and distinguish them from thermal fluctuations? And the way we do it, basically, so we will have these these particle hole pairs are doubly occupied side with an empty side with an adjacent empty side. And as you remember, we have this parity projection, so a doubly occupied side will also be detected as an empty side. So we would see these correlated particle hole pairs as correlated holes. And we can assign to this occupation number a parity. So this, we have a parity -1 for an even atom number and a parity +1 for an odd atom number. And the quantity we use to characterize, to quantify these correlations are the nearest neighbor parity correlations derived out of this parity. So that's the average value of the product of the two adjacent on-site parities minus these uncorrelated these on-site parities in which we subtract the uncorrelated thermal fluctuations. And here you can already see for this particular value of J over U, you can see in this sample by eye that we were able to catch a couple of these correlated holes. And for more quantitative analysis, we did many of these pictures and varied the parameter J over U from the super deep in the mod insulator limit that's over here to the superfluid, and we saw the red points, that's the parity correlations along the axis where we had allowed tunneling, and the system, the lattice depth was rather deep along the other axis in order to completely suppress tunneling, and as we would expect, we don't see any of these parity correlations at all. So in order to understand this data, so the first naive interpretation is like first order perturbation theory, and one would expect for increasing J over U that these pair correlations emerge as J over U squared. That's what we roughly see with at the beginning for small tunneling, that's the dashed dotted line. But to describe the signal over the whole parameter range, we have to get our theory colleagues involved. So first we started the DMAG calculation with Leonardo Mazza from the MPQ did this for homogeneous system at 0 temperature. That's the dashed line which almost described the right shape of the curve but not the right amplitude of the correlations, and then a more involved calculation including the realistic temperatures, and the trap basically gave this solid line, and that reproduces our data fairly well. And with this curve, basically, we have shown that we indeed could see the quantum fluctuations and clearly distinguish them from any thermal fluctuations that were basically subtracted out here. Okay, and we could do something more rather than only observing the correlations as they appear statically. We could also see the spreading of the correlations in a quantum body system, and for that we changed the setting a bit. So right now we try to excite the system in a certain way. Again, we stay with the 1D systems and we do a parameter quench. So we start with a system deep in the mod insulating regime with U over J equals 40, and then within a time much smaller than the inverse tunneling rate, we ramp the system to a point which is close to the critical point. And the general philosophy of these quench experiments is that we start with a system in an eigenstate, and then as we rapidly change it, the system is no longer in an eigenstate for the new Hamiltonian, and we have a time evolution under this new Hamiltonian. And what we are looking at, again, we again have a look at these parity correlations, but right now we don't look at parity correlations only for neighboring atoms, but we evaluate parity correlations for different pair distances, as you can see here with the index d, and we see, and in addition we have the parameter t, so we want to see how these parity correlations evolve over time. And that's what you see here in the following data set. This is the parity correlation for different pair distances 1 to 6 as a function of the time. And what you can clearly see that we have this maximum of the pair correlations evolves through the system in time, and we have a light cone-like spreading of the correlations. And that's quite intriguing, we found when we first saw that. But then, we immediately started to ask our theory colleagues, and Corinna Collard has greatly worked out many theoretical models to understand this in detail. So it can be, like, the data can be readily understood with a time-dependent DMRG calculation with rather simplistic assumptions of the system, which is infinite and homogeneous at 0 temperature, and even this theory reproduces our data fairly well. This is the green curve, and our theory colleagues even came up with a more sophisticated model to understand what's happening after these parameter quenches. Basically, what happens after the quench, the system sort of is excited, and fermionic quasi-particles emerge, and they basically emerge everywhere from every single lattice site, and these fermionic quasi-particles are correlated particle hole pairs, and they're emitted with opposite momenta. That's visualized here. These red and blue balls are the quasi-particles, so the W-occupied sites and the holes. So this is only approximate. In reality, the W-occupied sites have a small mixture of a hole and vice versa. But to first approximation, this is a valid picture. And you must imagine that these particle hole pairs, they are emitted basically from every single lattice site simultaneously, and they are entangled particle hole pairs. So you have a hole emitted to the left plus and a W-occupied site emitted to the right plus the inverse. And these particles and holes propagate ballistically with different velocities through the system, and they follow a well-defined dispersion relation, and that's basically why you see this wave packet-like behavior. So this dispersion relation also involves like Bessel functions. That's why you see this second maxima, which you can almost recognize from our data. And this dispersion relation also describes that the amplitude of this maximum of the correlation decreases. And this spreading of correlations has some rather fundamental implications for quantum antibody systems. And well, this interest started basically already in 1972, where Lieb and Robinson put up their famous theory and a theorem stating that perturbation can propagate with a finite sort of speed of light if the evolution is governed by local Hamiltonians. And this theorem had wide-ranging implications for condensed matter theory and quantum information, and our experiment was basically the first observation, the first direct observation of this correlation spreading in a strongly correlated system. Okay, so how much time do I have?
5 minutes.
5 minutes, okay. So then we have to move a bit quick. I will start by showing you a technique how we can address individual spins in the optical lattice, and then we will use this technique to deterministically prepare single spin impurities and see how this single spin impurity propagates through the system. Okay, the single spin addressing, basically we use everything's already in place, so we have the high resolution imaging system, but instead of just using it for observing, we shine in a laser beam from the backside of the imaging system and focus it onto individual lattice sites, and with that we create a diffraction limited spot size that we can move over the atoms in the optical lattices by the help of this two-dimensional scanning mirror. And we, as a wavelength for this addressing beam, we use a magic wavelength with a certain polarization that deforms, deforms the lattice in a certain way. So we consider the two hyperfine states, these two hyperfine states of rubidium, and this magic wavelength only acts on the atoms in the upper hyperfine state. And the general idea of this addressing scheme is that we shift one of the atoms, we focus it onto a single lattice site and shift the addressed atoms into resonance with an external microwave field that can drive the transition from between the two spin states, flip the spin, and all the other atoms which are not affected by this laser beam basically don't see the microwave, and the spin remains in the initial state. Okay, let's do the experiment. So we shine the laser beam onto a single side, do a spin flip, and then do this repeatedly again and again for a couple of spins. So in order to reveal the spin flipped atoms, we apply a laser pulse that removes all the atoms in the upper hyperfine state, and then we are left with the following. Here you can see the initial mod insulator, and here in which we have removed flipped 16 spins successively and then removed them. And well, here you can see that it works quite beautifully. And we also did a more quantitative analysis where we characterized the fidelity here as a function of the pointing offset between, of the addressing beam. So 0 pointing offset means we directly hit the lattice site, and 0.5 pointing offset means we hit in between two lattice sites. So we can see that if we do everything right, we have a very high spin flip fidelity of 0.95%. So we just count the number of holes as a function of this offset, and we see when we go away from the center, we see that this probability drops to a background that's given by the thermal holes of only 6%. And what's quite remarkable is that this curve has a width of 300 nanometers and, more interestingly, an edge sharpness of 50 nanometers. That has to be compared to the diameter of this addressing beam of roughly 600 nanometers. And this proves that with this technique, light shift plus microwave, we have realized this a super resolution technique that allowed us to reach a sub-diffraction limited addressing resolution. And we can also produce, just for the fun of it, some nicer pictures in which we start with all the atoms in the upper hyperfine state, then flip a couple of spins, and then remove the non-spin flipped atoms, and then we end up with the following. So this is a deterministically prepared chain of 15 atoms. And as we are physicists, we couldn't resist of preparing a psi. That's a psi out of 16 atoms. Okay, now that's very nice, and we can use that to deterministically create a single spin in a one-dimensional mod insulator and see how this propagates. In order to do that, we slightly refined the technique. Instead of using a single laser beam to address only one atom, we sort of want to parallelize this technique. And we now use, instead of a single laser beam, we project a line onto the atoms. And we use a digital mirror device to create a line-shaped laser field that we basically project, as for the single beam, onto the individual atoms. So we use a single line and prepare a series of use 1D systems, and we create a series of 1D systems with one flipped spin at the center. So we can do other patterns. I skip this, and this multi-site addressing with this line-shaped beam works almost as well as the scheme I've already shown you. Let's go right away into the experiment. So we basically start by flipping a single spin, and this spin, when we want to see how this propagates, and we do this in parallel. So we flip a series of spin in, again, 1D systems, or we consider, again, we are still in one-dimensional systems. So please remember that. And then the advantage is of this line-shaped beam is that we can not only prepare the initial state much faster, flip all the spins simultaneously, but also we can pin the spin flipped atoms. So we do this spin flips in a rather deep lattice to completely suppress tunneling, and then we ramp the lattice to a desired value as we want to see the behavior of this impurity dynamics when we go across the superfluid to mod insulator transition. And this simultaneous addressing has the advantage that we can pin the spin flipped atoms, so we hold them in place and then can release them and start the dynamics very deterministically. And what we expect to see is like is for the case of large interactions U much larger than J. So we have usually a two-component Bose-Hubbard model that can be mapped into a Heisenberg model in this large interaction case. And basically we have this isotropic Heisenberg Hamiltonian, many of you have already come across, I guess, which involves this isotropic spin-spin coupling. And one can rewrite this term basically in using these spin, these operators of the effective spin, and this basically shows that the spins can hop from side J to side I, or the other way around. And the coupling parameter is the so-called J exchange coupling that's given by the single, the free particle tunneling J squared over U times 4. And this super exchange coupling is very similar to the Hamiltonian for the single particle tunneling. So the J exchange is just replaced by J, and here you have the single particle tunneling, as you have seen this term in the Bose-Hubbard Hamiltonian only. And this J exchange, you should know that this is for the parameters that is much smaller than J. So all the dynamics, what you expect to see for spin exchange dynamics, is much smaller and much slower than single particle tunneling. And the way we detect the system, there are basically two ways. The problem is our detection is not spin resolved, but you have seen, like for the single side addressing experiments, that we can simply remove one spin component and then image the rest. So we do the same here. So we have two ways of evaluating our data. One, which we call is the positive image, so where we remove all spins except for the impurity, and then just see where the impurity is after time. And then there's the negative image where we remove the impurity, and we measure this spin impurity as an empty side. And the one problem is that, as you have seen, that we also have thermal holes in the system. And when we do these negative images, we really don't know if we detect two holes, which one was the spin impurity. So, and we can solve this problem very elegantly. Basically, when we do this experiment and evaluate our data, we will only use the samples with one empty side. And then we know that this empty side, we can prepare the impurity with very high fidelity, that it indeed has to be the impurity, and the system has no extra excitations. And with this post-selection, basically, we can artificially select a zero temperature subset of the data. And well, let's have a look at the data for one particular value that's deep in the mod insulating regime. So we show the probability of finding the impurity at a certain position. This is the position in lattice side. So initially it is prepared at the center, and then you see after 40, 60, and 80 milliseconds the probability distribution. So you can very clearly see that it has evolved in time, and that the probability distribution clearly shows distinct minima and maxima. That's a clear sign for the coherent evolution of this tunneling process. And we can even understand the data with an analytical function. So this Heisenberg model can be solved analytically, and this probability is this Bessel function of that involves the super exchange coupling as a free parameter, and that's a fit basically with this model. So I think I have to come to an end. I thought I had 5 more minutes, but okay. So well, let me just have. So I will skip this, and this is the summary of this of the spin impurity dynamics. So we've probed the dynamics of the spin impurity all across the superfluid to mod insulator transition, and we could find a very good agreement with the analytic solution of the Heisenberg model deep inside the mod insulator limit, and in the superfluid limit this description breaks down. And we had to again ask our theory colleagues. In this case, it is Thierry Giamacchi from Geneva, who did T-DMRG simulations of the system. That's this green curve to describe and to understand the behavior in the superfluid regime, and that matches our data points fairly well. And indeed, we see that the dynamics in the bath of other spins. It's fairly different from the dynamics of the of free particle tunneling, which should, and this propagation speed basically should be 2 times j times the lattice constant over h that's up here, and all the velocities we have observed here are just much lower. Okay, I think I have to come to an end. So we have seen many experiments, and we could use the quantum gas microscope to probe strongly correlated systems, see dynamical effects, adverse individual spins with single atom and single site resolution. And there's a multitude of possibilities that one can explore in the future. So one can continue with exploring the spin dynamics, correlated tunneling of adjacent atoms, see how domain walls relax. In many groups are currently striving towards single site detection of correlated fermionic quantum phases, and also my new setup in Strathclyde is towards that goal. So there's a setup towards single site imaging of potassium and rubidium, in particular the fermionic potassium. One can use the local addressability to implement novel cooling schemes, and also the possibility of generating and projecting arbitrary light fields to deterministically remove regions with high entropy. There's the possibility, which we also have explored and are still exploring in Munich, about exciting atoms to Rydberg states, explore long-range interactions, observe crystalline ordering of the Rydberg excitations, and not talking about the huge possibilities this system offers for quantum information processing, as we have a huge array of individually addressable quantum bits. And there's a lot of things to do to explore these things to make a truly scalable system for quantum information. Okay, I think I have to stop, and thank you for your attention.